Ooh, here we are. There's the Earth. Remember our Earth, Sun, Moon thing? There's the moon. Let's see what's going on. Okay, the title of this video is Mass is Gravity. Mass is Gravity. What a weird idea. But this two objects are very massive. They have a lot of mass. So something happens that keeps this Earth spinning and the moon orbiting around the Earth. How can that be? What is there about the Earth and the moon that makes this happen? Well, as you watch this moon orbit, I think you can believe that the Earth is pulling on the moon, kind of like a string is pulling on the moon. But what do you think about the moon's gravity? Well, the moon is about 100 times less mass than the Earth, but it still has gravity. All mass has some kind of gravity. So, how does the moon pull on the Earth? What do you think is going on when we have tides in the ocean? That's the moon pulling on the water on the Earth that's causing those tides to come in and to go out. As the moon is overhead, then those bodies of water are actually being pulled by the moon. Now, how can we make this realistic? How can we figure out where we can get some numbers? Mostly in science, if you don't have numbers, you really don't know much at all. It's just kind of a guess. So I'm going to switch to a board where I can write some of these numbers and we can try and make some sense of that. Did you like that little screen? I thought that was nice. I'm going to talk about the numbers now. How can we get the numbers out of all of this stuff? I've got my handy dandy dry erase board, and this one is irritating because you have a overhead light shining up there and you've got that spot. So sorry about the low quality production here, but I'm going to push on anyway. Okay, numbers, numbers, numbers. How massive is the Earth? A lot. How massive is the moon? 100 times less. So, does it make sense that the moon orbits the Earth rather than the other way around? Yeah, I think that makes sense. But how are we going to crank some numbers out of it? You got to do some math. Got to do some math. And so it's physics is fun time, and we're going to do some math. What about the force of gravity? Seems like that's a force. What about the other forces in the universe? There's the strongest force that acts at a very small distance between the quarks that make up the protons and the neutrons, and they bind together for the nucleus of the atom. That's a very strong force. That's the strongest one. Then you have electrostatic forces. You have the forces of the uh, electrons spinning around. Hey, another little orbiting thing. But the orbiting thing for the electron going around the proton, that's not gravity. That's electrostatic forces. The positive proton, negative electron, opposites attract. That's the way that works. So gravity is kind of like that. I mean, it's a force that pulls the moon towards the Earth. Think of the moon as the electron spinning around the Earth, which is the proton. Well, enough of that, because there's a lot difference there. But gravity is the weakest. How could gravity be the weakest? If gravity is the weakest, how does it take this marker and pull it right down, right out of my hand? Pick up the marker. Well, the Earth is supermassive. And the title of this video was what? Mass is gravity, or gravity is mass. No mass, no gravity. So these things go together. Isaac Newton, smart guy, apple falling from the tree. Whether that's true or not, I really don't care. Let's look at it this way. I'm going to put an F up here for force. Then I'm going to put an equal sign. Then I'm going to put mass of the Earth and mass of the moon. I'm going to multiply those two together. You know how to multiply, don't you? Then I'm going to put this thing here, which is the division sign or a fraction here. And then I'm going to put a little d down here. And this is going to be the distance between the Earth and the moon. Not from surface to surface, but from center to center. That's going to be the distance. And then I'm going to square it. So that says that bigger the masses, the bigger the force. That certainly makes sense. But what about this distance? As the distance increases, then the attractive force decreases. So if the moon gets away from the Earth enough, it'll go find some other planet to spin around. And the moon is moving out. It's the size of its orbit is increasing by a centimeter or so. So in your lifetime, the moon's still going to be there, so don't worry about it. Distance, force goes down. How do we express the mass? The mass is in kilograms. Let my marker dry out there. The mass is in kilograms. Now, what's a kilogram? Well, if I had a kilogram weight here, that'd be about 2.2 pounds. My mass is about 80 kilograms, unless I ate too much holiday food, and then it's maybe up a little bit more than that. Mass is measured in kilograms. Distance is measured in meters. What's a meter? A meter is kind of like a yardstick, only about 3 inches longer. Yardstick, 3 inches longer. What's this measured in? What's force measured in? Well, we're nice and we say that we're going to honor Mr. Newton, and that's what force is measured in, newtons. How do we relate these things? Or how much force does Earth apply to 1 kilogram? Force equals ma. Mass times acceleration. So what's the acceleration, or what's the force that's being put on that 1 kilogram? Well, if we knew the acceleration and we know the mass, then we can figure out the force. We look at 1 kilogram, it's going to be accelerated towards the Earth at 9.8 meters every second. Meters per second per second. Wow, this is getting heavy. Let me slow down. Are you catching up? Do you have any questions? I don't hear anything. If you need to have a question, try the comment thing. That might work out. Anyway, if the acceleration is 9.8 meters per second, that says 1 kilogram is being pulled by the Earth by 9.8 newtons. So if we plugged 1 kilogram in here and the mass of the Earth, then that would come out to be 9.8 newtons. We'd still have to figure out this distance, though, because the distance is to the center of the Earth and that 1 kilogram mass. Is this enough for now? No, not quite. I think so. That shows you the relationships. Is this going to give me the right numbers? No. Put this big G in here as, just call that a fudge factor or gravitational constant. This is the magic number that will make all of these kilograms and meters show up as a force in newtons. I'll stop here and see you on the next video. Keeping it short and sweet.